Yep, good.
Hi, I'm Vish. I think in today we'll discuss a little bit about in this today's world there's like this massive big LLMs where everyone thinks that we need to have like huge infrastructure or huge investment to train even a simple model. And I think I try to like challenge that and see if we can even train a very simple models with like a consumer side GPUs, which costs less than like $600, you can imagine. And can you get like some decent results? Um, and everyone has to talk like in the AI community, everyone was like, oh, I tried to train the model. Everyone was like, oh, which H100 do you have? Like how much
Mm,
money you
mm,
spend?
mm,
And I was like, I think it's not needed if you want to train like a smaller models, but if you're trying to train something like I don't know, Gemini 3 or like something bigger, Opus 4.5, you
mm,
probably need like a huge infrastructure because those models are like, I don't know, 600 gigabytes, 700. We don't even know the size of the model. But
mhm,
if you want to try to train some decent models, I don't think we need that infrastructure at all. So I wanted to try this out because to see the feasibility, how much longer it takes to train a decent model,
mhm,
how much memory it takes, what are the different tricks and um, uh, things you need to like implement to make sure your GPU is used fully, you're
mhm,
using your um, like a RAM for the preloading or the pre-fetching of the data itself,
mhm,
how much data you can train on. And as you can imagine, like in the today's models, like the context size is like a big thing because bigger the context, you can train a bigger the model, or the
mhm,
batch size is also like one of the important thing. But all of these are restrained or like
mhm.
need to be changed as based on how much big of a GPU you have.
Got
So
it.
in
So,
this, go ahead.
sorry, so just to set context, you're focusing on training today,
Mhm.
not inference. Within training, the reason we are looking at a substantially complex class of models and reasonable number of tokens, context size, etc., is that if we can train on a reasonable budget, then it opens up innovation or a lot of more people can try things apart from being those few big labs which have tons of money, right?
Exactly. And I think I can show you some of these things like where you can do some of these studies to really show like improvement in even in the small models. And like architecture can help you, like some PyTorch tricks can help you to make these things. Uh, so definitely to your point is like even if you have like one person, they can train the model and like get a decent performance.
That's good. Go ahead.
Cool. So here, what we wanted to train was like this GPT-2 model, which I think came like a long time back. I think this was one of the first model which brought us into this LLM AI like new era, I would say. And this was the first model where also published by OpenAI to like give it to public. They also have a technical paper on this. They also had the weights on this and some code on this. And I think Andhra Karpati also made a video. Like I don't remember how long what it was, but I think it was a whole day I spent like watching the video and see what it is doing. Um, but there are like a multiple like the tiers of this GP22 model. So they basically use different size, and like I went with the smaller size. I think they call it like a tiny GPT-2 or something like that, which has like a 124 million parameters. And my goal was to train this model from scratch. And I have like a very fairly simple GPU RTX 5080. It's not even the state of the art currently. I think RTX 6000 is something is out, which is like I think 20,000, and the 5080 thing is like $600 or something like that. Basically, I use this for gaming, nothing else. But I wanted to train some AI models and see what happens. So the next thing I wanted to probably focus more on is like, hey, what data set you want to train on? Because I think like these big labs have like gigantic data sets as well, like internal, external, internet as well. And they probably also fine tune the data set by a lot of like data processing, cleaning, sanitizations, and all those things. So here I try to train it on like a this data set called like Shakespeare, which is basically collection of all the Shakespeare writings. It is like archaic English, as you can imagine. The grammar is old and all those things, but I think it doesn't matter for the like the LLM. It will just give you what input you give as an output, and I think does a fairly good job. Um, and I think the data size here, if you see, it has almost around like 56,000 tokens or something like that overall, and it's not a huge data set. Um, but there is another data set which you can actually use, which is a little bit bigger, which is also available open source. It's called um, um, PineWeb.
Okay.
PineWeb is, and there is a PineWeb Edu.
Okay.
PineWeb Edu is basically all the books which are open,
Okay. Okay.
scientific books, and all those things. And those are probably like a higher quality data set, as you can imagine, because those are like reviewed by a lot of like different peers, because these are books, academic books, papers, and all those things. So the quality of the data is a little bit higher than that, and you can even train on that. I think I tried that on some of my model as well. From the model architecture point of view, I haven't changed any parameter here at the first stage. I just use as is like um, the original attention. It's not like the attention from 2017, but this is like just a decoder only architecture where people try to remove this like encoder and the intermediate stage where we go from encoder to decoder. I think you probably already know why people are moving towards the decoder architectures, because it's very simple to train, and just for the LLM, you don't even need this encoder to decoder information. And the another reason was like this having encoder decoder and making it bigger and bigger was not easy or not scalable. But when we
Mm,
have this decoder only architecture, they try
mm,
to like just stack like numbers and numbers of layers, and it was like very scalable. And I think the
mm,
OpenAI showed it. It is like, hey, instead of 12 layers or 12 blocks, you have like, I don't know, 124 blocks, and it will
mhm,
like performance will go up and up. You don't
mhm.
even need to change any data. You don't need to any change. So you just need to stack more. So that was the scaling
I
part of
see.
last 3, 4 years, as you can imagine.
I see.
And that was enabled by this decoder only architecture. Um, yeah, and then embedding dimension, I think it was default. I haven't changed the context length as well. Actually learn about this little bit, why this context length is a little bit important, but I'll tell you later in the
Mm,
talk about this.
mm,
And I never like imagine in that way as well. One other thing the this GPT-2 paper does as compared to the earlier original transformer is this causal self-attention,
mhm.
as you can imagine. Actually, we don't have encoder decoder anymore, so they got rid of the cross attention and all
Yeah.
those things. And the causal self-attention is very simple trick is like basically the next token just depends on whatever you see earlier, but you don't see the future. So they use this like a triangular mask to like
Yeah.
mask the next tokens, and the for the next prediction, the user only looks at the previous thing. So basically, the model is not able to like look in the future, or there is no label leaking or no cheating, as you can imagine. Um, then second thing I think is the positional embedding. I think this is very similar to the original paper. They're using this um, sine cosine transforms to like create this spatial information about like from the start of the sentence to the end of the sentence. And those are positional embeddings added directly to the input embedding, then given to the transformer. Nowadays, people are using different embeddings, call it like rotational
Yeah.
embeddings, rope. Those are like a advanced version of this. I think we can talk about that as well. Right? But I wanted to keep the same architecture here and just see the performance. How do we get? Um, and there are some like clever tricks. Sorry, people talk is like wet tying and all those things. Basically, we use the same embedding layer for final projection as well as the input projection. Because as you can imagine, like these models, the biggest things are like this feed forward network, which is at
Hmm.
the end,
Hmm.
and they are like so dense, and
Hmm.
that also creates a huge neurons or like a huge size of the model itself.
Hmm.
Nowadays, people are trying to replace that using mixture of expert,
Hmm.
and that helps at the inference time because not all the neurons will be active at the same time,
Hmm.
and you can actually run the inference faster using this gated mixture of expert. But that's the
I
latest thing. Yeah,
I didn't totally understand the reusing embeddings or tying the embeddings part, but I think you'll come to it later.
yeah, yeah.
Yeah.
Yeah. So we'll talk about the weight tag at
Mm,
the
mm,
like the when you go there. So the implementation, as I said, is like it's very simple. We started very clean state. The first thing was like, hey, how to build this tiny Shakespeare data. Actually, you can download this. I think
mhm,
Hugging Face has done a huge job or like impressive job to have all this data set as well as model. They
mhm,
have this like a tiny Shakespeare data you can download directly. Um, and then you can just write PyTorch data loader to get that data by batch, however batch you want. Um, then the next thing is like, what is the forward pass? It's pretty simple. Like you compute the logits. The loss is straightforward as well, the cross entropy loss. And then you're just calculating this cross entropy loss like for each token. And then when you have this loss, you just do the back propagations while computing the gradients, and then you use the optimizer. I think I used this Adam optimizer, which was
mhm,
also standard optimizer nowadays.
mhm.
Um, so the first thing I wanted to try is like, hey, let's get this like end-to-end training flow
Yeah.
right, see
Yeah.
how it works. So the first thing was like the biggest issue, as you can imagine, is the batch size. I think the OpenAI used like a huge batch size. I think it's like more than 1,000, something like that. And when I tried like even 8 or 12, I was getting like out of memory. But then
So
at four, I
yeah,
was okay.
I didn't thank you. I didn't understand how is it that they're able to do 1,000? Is it because they are able to distribute the training or
Yes. So
I see.
they use these huge GPU cards where each GPU card has like eight GPUs, and those
I
are
see.
H100 as well.
I
So
see.
they can distribute all this batches into different GPUs.
I see. I see. I see.
So they also use this trick called this gradient accumulation. I think I also tried that. So the gradient accumulation trick is basically what you want to do is like you can so you know this stochastic gradient is right. The
Yeah.
stochastic gradient is basically instead of learning on all your data, you
Hmm.
only select the batch and
Hmm.
assume that that is
It's
my last,
representative. Yeah. Yeah. Yeah.
and then go from there. So here in the gradient accumulation, what you do is like if your batch size is lower, the issue it becomes is like it may not be representative of your data,
Okay. Okay.
and your loss may like just oscillate all
Ah,
the time.
I see. I
So
see.
what you do is like, hey, I want to accumulate my gradient for n number of times, and for those n, we will have batch size of 4, and then you only propagate the backward propagation, or you only
Very
propagate the
interesting. Very
loss
interesting.
4 into n times. So basically, your model will be like a little bit better because now your whole data is representative, or your whole batch is representative of the data you have.
Mm.
So that's what I also tried. And the first thing was like 29,000 tokens per second. I think it's not huge, but it's I think something. And there is this tool from NVIDIA. I think it's called NVIDIA SMI, which is basically looking at like how your GPU utilization is. And I was looking at what was happening is like for the forward pass, like I was getting this like uptakes, downtake, uptick, down things like this, like step function change of my GPU usage because my GPU was always not active when I was training because it was taking some time to preload the data into the memory before you train. So that's some nice baseline, but it also gave like a decent performance from the quality point of view. But I knew that if I just want to keep this, it's gonna take forever to get my any decent performance if I want to train on the whole thing. So the next thing I wanted to do is like, hey, how do I optimize this from here? So the first thing was like it's pretty normal. Normal nowadays is like this flash attention. So the flash attention is basically optimized version of attention. It is not an approximation. So when the code from the CUDA, PyTorch, and the hardware they come up together to like make this like processing faster, basically. As you can imagine, when you're doing this cross dot product in attention, it's
Hmm.
probably gonna take you this O up n square memory,
Hmm.
which you need to keep in the storage of the GPU, and which is
I
like
see.
very not scalable. And
Hmm.
this n is depending on like how much context you have, right, or the batch you have.
Yeah.
The bigger it is gonna be, the worse memory usage is gonna be. So they they have this thing called like scale dot product attention, which is flash attention basically. And what they're doing is like instead of storing the whole metrics at the same time, they're storing the batch of the metrics and then do the calculations, and they're distributing it into the different GPUs of
I see.
like the part of the metrics. So one GPU is not calculating the whole metrics. The part of the metrics is calculated by the GPU, and then it is accumulated, and like you get the full metrics again. Um, and when they do that, they use this sliding window approach, and because of that, I think now their memory consumption is O up n instead of O up n square. Um, and because of the hardware changes from the CUDA NVIDIA as well, this is still faster uh, as compared to like the original one GPU where you have to like distribute and all those things.
But
Um,
you don't. You in your experiment, you just have one GPU, right?
yes, but even if you have one GPU, you can like do this sliding window approach on this one GPU. The only problem is it will be like
I
delayed a
see.
bit.
I see.
But the problem with the bottleneck is like if you don't have enough memory, you cannot do like the uh, attention anymore. So you have to reduce the batch size. So there is a trade-off here. Is like,
Got
can
it.
you
Got
increase the batch size and do the windowed attention approach or the
it.
scale attention approach? And because of that, then I could just like jump my batch size. I just changed like one line of code. I think is like instead of just doing the matrix multiplication here, I just use this self attention trick call. So as you can imagine earlier, you could just like do the um, multiplication or like a dot multiplication in Python. Instead of that, you call this, and there is nothing extra you need to do on top of it. And that should be the whole thing for the flash attention itself. But it's pretty easy. Then I could just increase my batch size from 4 to 8, and it didn't over like give me like this OM error. So that was the first thing. Yeah. So this is the second part. I think this is kind of like this moment I realized is like, oh, this makes sense. It's like the vocabulary size for the GPT-2 is like this odd number, 52, 50, 72.
Hmm.
And this
Hmm.
comes from this data processing, sanitizations, and the tokenizations and all those things, right? Like how you
Hmm.
create the
Hmm.
tokens and all.
Hmm.
And I
Hmm.
think this GPT-2 uses this like uh, 2 byte encoding. I think that's what they call it, like pair byte encoding, to
Like that, okay.
um, create these tokens, and that's how they got this number. But as you can imagine, your output layer is gonna be of this size because you want to predict
Yeah,
for each.
probability of each token. Yeah, yeah.
Exactly. But the problem is the NVIDIA GPUs are like this, have efficiency if your number is power of 2, because that's like the how hardware implementation. And as you can imagine, this is also the reason if you see any neural architecture, the
Mhm.
hidden size is power of 2.
Yeah, yeah, yeah,
And so like 8, 16,
yeah,
32, and all those things.
yeah.
And people try to keep that also in their output layer just to make it um, more efficient. So what we did was just did the padding, and basically there are like dummy vocabulary as you can imagine, and we resized it to the nearest multiple of 64, and that actually gave like a very decent performance improvement. Uh,
Sorry, you're saying you actually increase the vocabulary. So
mhm.
you basically are doing more work, but it is faster.
Faster, yes, exactly.
Very
So,
interesting.
and this the only thing I need to change here is the final data projection layer. That's also the biggest, like the layer as you can imagine, because it's a feed forward network and every component is connected to every other component of the previous layer. And I change that, and it becomes like significantly faster in the training just because of the memory alignment of this like power of 2 thing from the hardware itself.
I didn't understand. What only thing you had to change was that?
The final layer, the final projection layer, instead of like 52, 50, 70, we change
Yeah.
it to 5304.
Okay, okay. You're saying there's only one parameter I had to change and all. Okay,
Exactly.
understood.
Yeah. And now because of the memory alignment, we see the huge improvement. So that's one thing. And this was kind of like, this makes so easy to like understand as well why it is happening and why the hardware and the software needs to be in the same, like this like orchestra together to make it faster, I would say. Um, yeah, so that
we
was just a vocabulary.
we might be running out of time. We have, let's say, 3, 4 more minutes.
Okay, okay, sure. Let's go to the next one. I think this is probably the next biggest thing which we wanted to do. So, as I said, we talked about this NVIDIA SMI, which is a tool from NVIDIA you can use to see the GPU utilization over time. And I could see there is this like spikes when I use the GPU, then it goes down and all those things. So basically, it was telling I'm not using my GPU completely all the time, and there is inefficiency. And that inefficiency actually came from like this waiting for the GPU to load the next batch of data. Basically, it is telling is like, hey, I'm waiting for the next batch to come. And that was because my CPU was not fast enough to read the data and like put that into the GPU through the RAM.
I see. I
So
see.
this is also very standard nowadays in PyTorch data loader. People use this thing called like pre-page, and
I see.
basically use the number of more number of workers and are taking your data and trying to load that into the GPU or pin that to the GPU. And after that, I saw that now I'm using more and more GPU, like almost 99%.
Very nice.
It
I'm
was
proud
like
of you.
30% or something like that. And that jumped my tokens again almost double than what I was using earlier. Um,
So when you say more number, I'm sorry if there's a new question, but more number of GPUs, are you looking at flops or are you looking? I know you said GPU utilization, but was I
yeah.
think there's just GPU memory. There's yeah, what are the
So it is like basically the utilization is calculated based on how many tokens I'm processing per second. Which is you can convert that into the number of flops used or the clock cycles used by the GPU itself.
I see. I
But it's
see.
easier to understand from the tokens point of view. That's
Yes.
why I'm
Yeah.
presenting from the
Yeah.
tokens per second. So the prefetching just help. And how do you define the number of workers? This should depends on the number of cores you have in your machines.
I see.
But I don't think you need to utilize all the cores because you're probably doing some other work on the side as well and not
I
just
see.
like doing the GPU training. So just use the four. I had like 8 cores. So instead of using all the 8 cores, I used the four.
I see.
Um, yeah, that's the only thing. The next thing is very simple as well, which is the Fuse Atom implementation. This is also optimization from the PyTorch itself. Basically, they're using these Fuse kernels, and these are like basically big single CUDA kernels and removing the CPU overhead of optimizing the backward propagation. There is just one flag. You just said like, hey, use the Fuse kernel. There is no um, like the performance implications or anything here. Um, so that was it. That improved some CPU overhead and like made it faster. And the last thing is the touch compile. I think this is also like probably the biggest thing from PyTorch, which is basically like this just-in-time compiler, where what they're doing is like optimizing your model to be like more um, like efficient. And how they do that is they fuse the multiple operations into like a single operation, so that you don't have to like move the memory from one tensor to other tensor, because as you can imagine the neural network is just like bunch of mathematical operations, some linear, some non-linear, and every time if you keep moving the memory tensors, it will be expensive. So what they do is
Interesting.
like they just fuse like some of the operations like the layer norm and the linear layer into a single operation, and that gives like a huge
Very interesting.
improvement. And now then I went from 63,000 I guess to 92,000 tokens per second, and then I could like train faster. And it was not like I could train like 150 iterations, which was one epoch, like the old data, and that took me like 13 minutes. That's it. That on the start tiny Shakespeare data set. But I
Wow.
did ablation just to understand how much each of those are giving. And the biggest was the compile thing. Obviously, the PyTorch and the CUDA worked together to make it possible. Then the flash attention was the second biggest thing, because I think that's like the
Hmm.
most
Hmm.
expensive operation. Then the data loader and the other optimizations like the Atom,
Hmm.
and all those things help as well. But
So,
go
if
ahead.
I'm reading this, did flash tension go from 63.5 to 67.5, or is it like 29 to?
29 to 63.5. Yeah.
No, no. So,
I
is
think I
flash?
put the sorry, go
Mm,
ahead.
yeah, yeah. So, is flash attention, and how should I read the effect of flash attention? Is it 67.5 minus 63.5 K?
Yes.
Okay, okay,
So
okay,
this is also a linear number, right? It went from 1 to 2 to 2 to 3.
okay, 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 okay. So, in that sense, the biggest impact was the data loader,
Yes. Yes.
and the I think you said also the power of two thing.
Yes. Yes.
Very nice. All right. We are 2 3 minutes over time, but like now that, yeah, you talk a little bit about the next steps, I guess.
Yeah. So the next step is, I guess, we talked a bit about like how to use this rotational positional embeddings. These are like the next big thing, because as you can imagine, like the context window is getting bigger and bigger because we want to train bigger models, and because of this, like this stationary information from the earlier positional embedding, now the start of the sentence and the end of the sentence is like million parameters away or the million tokens away, and that creates like this difference. But in the language, most of the information is in the locality. Like if you're talking,
Yeah,
like
yeah,
the
yeah,
context right now is like what I talk like 30 seconds now and after,
yeah,
right? It doesn't
yeah,
matter what I said like 30 minutes ago. It doesn't matter
yeah,
that much, I would say.
yeah, yeah.
So this positional embedding is basically trying to do this locality bias inside the input itself that actually makes it way better. The model could learn that, but I think giving that as an input is way better than model learning on its own, right? Because it's like easier for model. Excuse me. As you can imagine, like if you give a better feature, the model will learn like way better than like
Interesting.
you give like some raw features to the model. The next thing is like this RMS norm and like changing this.
Hmm.
from the layer norm.
Yeah, no.
This is also very simple change. The layer norm is like this doing this mean adjustment, and the RMS norm says that I don't need to do the mean adjustment because the LLM is very good at doing that. And it actually saves almost 30 to 40% calculation of the mean and all those things.
Wow.
Um, and there is no impact on the quality of the performance after that. Then there's like a activation function change.
Mhm.
This is also very simple change, and this adds a little bit more parameters, but it's improves the performance of the model. And these are all like not like just improving the token, but now I'm thinking also about how do we improve the model. Basically, this
Yeah, yeah, yeah.
GPT-2 was came in I think 2029, 2020 or 2019 or something like that, and after that it's been 6 years, and the
Yeah.
AI is moving so fast as you can imagine.
Yeah.
Um, The group
Okay.
QA attention is more on the inference side, how to make it faster and all those things. Mixture of expertise also on the inference side. It may have some impact on the training, but you need to run the ablation studies to understand like how much is it impacting. The
Okay.
group QA attention and is kind of like trying to reduce this KB cache, as you can
Okay.
imagine. Um, because you don't need to have this key value every time, like replicated and all those things. You only need to replicate the query
Okay.
which is input. Yeah. But we can talk about all this in the
Yeah,
next
yeah, yeah.
talk
I
as
was
well.
gonna say, it's a good, ad, I guess, for the next video. Thank you. So, yeah, and when you create, I saw you'll have the linked GitHub repository as well.
Yes,
I'm
yes.
guessing, sounds good. All right, I'll stop recording.